Hey everyone, in this lesson we are going to solve the problem 3 on the collection of problems about pushdown automata. So, in this problem 3 we have that they are asking us to construct and to build this pushdown automata that recognizes this language, which is the language where we have the same amount of A's and B's. So basically here we have a little and a brief description of this problem. It is said, write a deterministic uniquely accepting PDA, pushdown automata, recognizing the words over the alphabet A and B, such that the number of occurrences of A coincides with the number of occurrences of B, right? So basically the idea in here is that if a given word W belongs to this language, then the PDA or pushdown automata will accept this word. It will be an accepting word. And in the same way, if a given word doesn't belong to this language, then our PDA, our pushdown automata, won't accept this word as a valid word for this automata. So before starting building this PDA, we are going to see some words that belong to this language and some that do not, so that we fully understand this language. So basically, our language consists in the words over the alphabet A and B. Yeah, we have the two terminal symbols A and B, and the idea is that we have we must have the same amount of A's and the same amount of B's. So that if we have 3 A's, we must have 3 B's. And keep in mind in here, okay, on the other side with the previous problem that we have solved, they do not ask the word be in a specific order or in a specific structure, so that they are not saying, hey, you have or you must have first the A's, then you must have the B's then, or you have the B's first, then you must have the A's at the end. So they don't do anything and they are not specifying anything like that. The only condition that we have in here is that we must have the same amount. So the only thing that we care about is how many A's and how many B's there are in the word. So now let's consider, for instance, right, the word AA, B, B. So is this word an accepting word? Well, let's count how many A's we have. We have 2 A's. How many B's? We have 2 B's. So since we see that the number of A's is the same as the number of B's, which is 2, then this is an accepting word. This word belongs to the language L, right? So our PDA, or pushdown automata, must accept this word. Let's continue. Consider now the word, for instance, right? A, B, AA, B, A, B, B, in the sense that we have 1, 2, 3, 4 A's and 1, 2, 3, 4 B's. Now, just consider this word. Is this word a valid word? Or does this word belong to this language we are studying? Well, we only need to count how many B's we have and how many A's we have, and then just compare if they are the same amount. So let's count up how many A's. We have 1, 2, 3, 4 A's, yes? So the number of A's is 4. Let's count up how many B's we have. Well, we have here, right, 1, 2, 3, 4 B's. So the number of B's is also 4. Since the number of B's is the same as the number of A's, then this word is a valid word and it does belong to our language. So here, it doesn't matter that we start with the A, then we have the B, then again we come back with the A's, then again we come back to the B's, then again with the A's. This is something we do not care about. So basically the structure of the words aren't something that we need to consider in this PDA. Only the number of the occurrences of this given symbol, right? So it is true that there are problems where the structure is given for the language, yes? For instance, if you have the language A to the N, B to the N, this language, for the N greater or equal than 0, this language is saying that we must have the same amount of A's and the same amount of Bs, and also we must have first the A's, then the B's. We cannot have first the B's, then the A's, or 1B, 1A, 1A, 1B, yes? However, in here, in this problem we are considering now, it is possible. We only care about the number of A's and the number of B's, right? So before jumping onto the words that do not belong to this language, just consider one last word, which is the word empty word, yeah? Remember that if we write the empty word, okay, this is basically saying that we haven't read any A and we haven't read any B. So we do not have any A and we do not have any B. So how many A's and how many B's we have in here? We have 0, right? How many A's we have? Well, we have no A. So the number here of A is 0, which is also the number of B's, since we have no B's. And keep in mind that with the empty word, this is satisfied, right? So with this, we arrive to the conclusion that the empty word does belong to the language L. Okay, it is an accepting word for this language. Okay, so let's consider now another set of words. Just consider, for instance, the word AA, B, 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 right? So is this word an accepting word? Well, we can count how many A's we have, right? We have 2 A's. How many B's? Well, we have 3 B's, yes. So in here, we see that the number of A's is not the same as the number of B's. So we come to the conclusion that the condition is not fulfilled, the condition is not satisfied, yeah? And since the condition is not met, then the word is not a word that belongs to this language. So it doesn't belong to the language L. So our PDA, our pushdown automata, must not, yes, it mustn't accept this word as an accepting word. The same goes for the word, for instance, AA, yeah, or for instance, B, yes, let's just start with the B's, for instance, BAA, B, A, B, 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 right? So what is happening with this word in here? Well, we can count how many A's we have, yes? We see that we have 1, 2, 3 A's. So here the number of A's is 3, right? And we can also count how many B's we have. We have 1, 2, 3, 4, 5. So we see that since the number of B's is 5, okay, these are not the same, so the number of A's is not the same as the number of B's. So basically this word is not a word that belongs to this language. And this is basically the idea of this language. We see that it is a very basic and simple idea. We just have to verify if we have the same amount of B's and the same amount of A's in the word, yes? So once we know fully how this language works, let's start with the construction, yes, of this automata. So now we see and we know, we have understood which languages belong to this, or in this case, which words belong to this language and which words doesn't or do not belong to this language. Once we know that, we can start constructing this automata. We always recommend the student that first let's try to understand deeply the language, yeah, because if some student starts trying to build the PDA before understanding deeply and fully the language, okay, there's a high possibility of errors, yes, and incorrect steps in the process of the building of this pushdown automata. So now we have understood fully how this language works and which words this language accepts and which words this language does not accept. So let's start with the construction of this PDA. So remember that in any PDA, right, in any pushdown automata, we have a stack, right? So initially we have a given stack, and at the top of the stack we have the Z. This is the neutral element, yes? And whenever we do a transition, we can push elements onto the stack. And by default, whenever a transition is done, the top of the stack is going to be popped. Yes, do you remember this from the classes on the theory, yes, of the pushdown automata? So it's important. whenever we do a transition, the top element is popped. And if we do not want this to happen, and we do not want to modify the state of the stack, we can push the same element. In the sense of, if I have the element Z at the top of the stack, and I don't want to pop this element with this transition, I can push it so it is popped and then push it again, so nothing is modified. Yeah. So what is the behavior of this PDA? Well, here the idea is that we have to verify that we have the same amount of A's and the same amount of B's. And the idea here is that whenever we read a given symbol A, yes, and we have either Z as the top of the stack, then we are going to push 1A. So here the idea is that if we read 1A, then we have to push the element uppercase A. So this is basically a variable into the stack, right? And this is the terminal symbol that we are reading. In the same way, if we read the B, the terminal symbol B from the input, we are going to push the element B. Yes? Now, what happens? This is basically when I have Z as the top of the stack, yes? What happens if, for instance, I have A as the top of the stack and I read 1B? Then I have to pop. I have to pop this A because it gets cancelled with this B. And in the same way, if I have B as the top of the stack and I read the A, I have to pop the B. So let's see how we do it, yes, and how we do this step by step. So initially we will have a starting state, yes, or the initial state for this automata. Okay, this state represents that we haven't read any element from the input, we haven't read any symbol yet, yes. So what happens in here? Yes, let's first define that this is the initial state. We do it with this arrow. Okay, when we write this arrow to the node, we represent that this is the initial state, right? And remember, since we have explained before that the empty word belongs to this language, yes, since the empty word belongs to this language, then our PDA or automata must accept this word. So this is basically saying that the initial state must also be an ending state or an accepting state, right? So in here we can just say, okay, since we know that the initial state is also an accepting state, we can represent this state to be an ending state like so. Remember that if we draw a inscript circumference into the node, yes, this inscript circle, it means that we are defining that we have an accepting state in this node. Yeah. So now what happens when we start reading elements from the input? Yes. So basically I will define a new state. Let's just say n. It can be any name you want. Yes. And this state is basically for the readings. So I start reading elements. Okay. So imagine that I am in the initial state, this state, and I read from the input, yes, the element A. So basically, initially, which is the element that I have at the top of the stack? Well, we can see that in any PDA, the initial element at the top of the stack is the Z, right? Is this one, the Z, the neutral element. So now, we must imply that if I have Z as the top of the stack and I read the A, then I have to push one variable A. Since, and the same way that we have explained in the blackboard. Yes, if I have Z as the top of the stack and I read terminal symbol A, we must push the A. So we do it, yes, we push the A. But remember, in any transition that we do, the default behavior and the default action for the PDA is to pop the top element. But we do not want the top element to be popped. Yes, this Z, we do not want this to be popped. So we need to also push it, like so. So the action is that we push, and the condition is that we read the A, with the Z as the top of the stack. Remember that in any transition of a PDA, we have the condition, which is the left part on the vertical bar, and the action, which is the right part. Yeah, so now, as we have explained in here, The condition is that I have Z as the top of the stack. I read the terminal symbol A, then we push the Z. So with this, we avoid popping the Z, which is the element that was at the top of the stack, and then we push the A. Okay, and this A is basically because we have read the A. And in the same way, in an analogous way, we see that if I have Z as the top of the stack and I read the B, then I push the Z again so that it doesn't get popped, yes, and I push the B. It's very important to remember the fundamentals of the PDAs because we have to know that within every transition that we do, in any transition, the top element is popped. And to avoid this, we push it again. This is what we're doing now with the Z. Okay, and then we push the A if we read the A, or we push the B if we have read the terminal symbol B. Okay. Now, what do we do now in this state N? So we have said that this state is a state where we start reading elements. Yes. So what happens? We have lots of cases in here. In fact, we have 4 cases. The first one, okay, imagine that I have read given A 2 times. Okay, imagine that I have the word, imagine this word, A, B, B, B. So as we have said, if I am in the initial state S and I have Z as the top of the stack and I read the element A, the input A, the symbol A, we push the A. Yes. Now what happens if I have A as the top of the stack and I read the A? Well, I have to push another A. Yeah, I have to push it. So I read this A, I push it. I read this A and I push it. Yes. So how we do it? Well, then in the transition in here, we just define this. If I have A as the top of the stack and I read the A, I push anyway, but I do not want to pop the A that I had before. I do not want to pop it. And if I do not want to pop it, I have to push it again. So this first A that we push is the A that we had before. And we want to avoid this to be popped. And we push the new one, which is the new A that we have read, right? And the same way goes for the B's. If I have B as the top of the stack and I read another B, then I push the B that we had before, so it doesn't get popped, and I read the new B also. Yes, this is the new B, like so. Yeah. Now, what happens in this case of this word, and in this example, this will allow us to explain also the analogous way and analogous case and situation. Yes, the analogous case of this one is basically the 3Bs and 3As. Yes, and you will see that it's the same behavior and the same mechanism, but basically it is analogous. Now, what happens when we read this B in here? Yes, we are reading this B, and we have the A as a top element. Then, since we have A as a top element, and we are reading the B, and we must have the same amount, for every B that I read, I have to pop the A, right? So basically, if I have A as the top of the stack, and I read the B, I have to pop this A. And remember, by default, the behavior of the PDA is to pop the top element. So we do not want to do anything, we just pop it. So we can leave the action with a blank. If we leave the action with a blank, we do not push anything, we just pop the A. Yes? So like so, the behavior is going to be, I read this A, then I pop this A. Sorry, I read this B, I pop this A. I read the second B, I pop this second B. I read the third B, then I pop this third B. So at the end, when we have read all the elements from the input, yes, all the symbols, and we have Z as the top element, then this word is going to be an accepting word. Yeah, and in an analogous way, it goes for the Bs. Yes, in this case, in here, we will have 3 Bs in the stack, and for each A that we read, we are going to pop the Bs. Yes, like so. So let's just consider these 2 cases now. If I have A as the top of the stack and we read the B, then we just pop the A. So we do not push anything, we just leave a blank after the vertical bar. So the action is a blank, so we basically pop the top element. And in the same way, if I have B as the top of the stack and I read the A, I pop the B. right? Like so, yes? And finally, if after all this we have Z as the top of the stack, like here, in this case, it means that my word is an accepting word. It belongs to the language. So now I have to go to the state S, which is the accepting state for this automata. Yes? In this pushdown automata, we only have one accepting state, which is the initial state S. And like so, we have Z as the top of the stack, and we just push it again. So we don't do anything at all. Yeah? So you can verify with this PDA that for any given word on the input that belongs to my language, in this case it has the same amount of A's and B's, then the PDA, okay, will accept it. And remember, when does the PDA accept a given word? Well, a given automata accepts a word if after reading all the elements from the input, we end up in accepting state. Yes, so let's consider this example of 3A's and 3B's. We have seen that this is an accepting word. Yes, this example in here, 3A's and 3B's is a accepting word. It does belong to the language L. So let's verify that we end up in the ending state. So initially, we start from the state S. We read the first A, so we push 1A. We read 2A's, we push 2A's more, so we have 3A's in the stack. Then we read 3B's, having the A as the top of the stack. So we pop 3A's. So since we have read all the elements on the input and at the top of the stack we have the Z, we must do this transition and we go to the ending state S. So after reading all the elements from the input, we end up in the state S, which is an accepting state. Yes, and since this state is an accepting state, then we can conclude that this word is an accepting word. Yes, it does belong to the language L. So in essence, this is the solution for this problem 3. We see that this is the correct pushdown automata that recognizes the language over the words A and B, such that we have the same number of A's and B's. Also, we remind the student that he can check the statement of this problem as well as its solution in the resources of this lesson. In the next lessons of this section, we will work with more advanced problems about pushdown automata.